So again, welcome everybody to this online session of the 2023 Pacific Causal Inference Conference. This session includes only two speakers, myself and Zichao Zhang will talk after me. We both have around 25 minutes, including some questions that we can take at the end of our talks. All right. I don't think anything relevant is written on the chart. So I guess I can go on and share my screen and start my presentation, right? So again, my name is Fabrizia Mealli, and as of September 1st, I moved from the University of Florence to the European University Institute, and the talk that I'm going to present is joint work with Laura Forastiere, Alessandra Mattei, Giulia Pescarini, Rosemary Fiaccone, and Mauricio Barreto. And in this work, we propose to use a Bayesian finite mixture approach to clustering to select subpopulations for which we can draw valid causal inference in regression discontinuity studies. So as probably many of you know, regression discontinuity designs are known as quasi-experimental designs where the treatment status changes discontinuously according to some underlying variable, usually named the forcing or the running variable crossing a threshold. Examples of these designs arise in many settings, including education, economics, public health, and for example, in environmental health studies, and specifically in studies where air quality regulations are assessed, typically treatments such as power plants closing or traffic restrictions are assigned based on pollutant levels, typically the PM 2.5, crossing a given threshold. And essentially, the basic ideas underlying exploiting regression discontinuity rules is that units with values of the forcing variables in a neighborhood of the threshold receiving different levels of the treatment are almost as good as randomly assigned, so that if we, let's say, contrast them or compare them, we should gain information and valid, and we can draw valid inference on causal effects. We usually distinguish between sharp and fuzzy RDDs. In sharp RDDs, as the settings that we are going to consider in this talk, treatment assignment and treatment received are essentially completely confounded, and they are a deterministic step function of the forcing variable. So namely, all units with a value of the forcing variable on either side of the threshold either receive or don't receive the treatment. Whereas in fuzzy regression discontinuity designs, treatment assignment still depends deterministically on the forcing variable, but treatment assignment does not coincide with treatment receipt. So we have essentially a discontinuity at the threshold in the treatment probabilities, but the jump, this discontinuity, so the jump in the probability is not equal to 1. So there is the discontinuity, but again, the probability does not discontinuously change, going from 0 to 1. So the motivating study that I'm going to also to show the results of our proposal with it's the evaluation of the Bolsa Familia which is a social welfare program of the Brazilian government that has already come to an end, is now replaced by a new welfare program. The objective of this welfare program was the reduction of, in general, of both short-term and long-term poverty through essentially conditional cash transfers. And the specific causal questions that we wanted to address, also working with these colleagues, epidemiologists in Brazil, was assessing the causal effect of this program on specific health outcomes. And again, more specifically, we are going to consider as an outcome leprosy cases in a family. So just hold on a sec. I want to move these over here. Sorry. Okay. And again, this Bolsa Familia allocation rule can be described as a regression discontinuity design in that first of all, a family to benefit from the program must register in this Cadastro Único and meet some eligibility criteria. More specifically, we are going to be using data on families who applied for some welfare program and therefore registered in this Cadastro Único in 27 and 28 for the first time. Eligibility for the program follows this rule. The per capita household income, which is our forcing variable, must fall below a prefixed threshold, where that was 120 Brazilian real in 2007. Here we are going to focus on intention to treat effects of eligibility status, and so we will view the evaluation of this program as a sharp regression discontinuity designs with respect to income eligibility. I'm making these sort of note just because not all families with a monthly per capita household income below 120 actually receive the Bolsa Familia, because essentially there are oftentimes delays in application approval that in principle makes these allocation rule more similar to a fuzzy regression discontinuity designs. But again, we focus on intention to treat effect rather than the effect on the actual receipt of the benefits, because this allows us to avoid making further assumptions, like, for example, the exclusion restrictions that would be required for estimating the effect of receiving the benefits. We, again, concentrate on the problem of instead identifying a subpopulation of interest and also account for its uncertainty with the proposal that I'm now going to explain. In fact, traditional approaches to the analysis of RD designs view the let's say these designs as irregular, and specifically irregularity comes from the non-probabilistic assignment mechanism. And so in the usual RDD settings, the only stochastic element is the sampling of the units, and focus is on the causal effect at the threshold for a hypothetical infinite population. So typically, smoothness assumptions are invoked on the relationship between the potential outcomes and the forcing variable. And under these assumptions, a jump at the threshold can be interpreted as a causal effect. Typically, inference in such designs relies on local polynomial regression methods with their asymptotic property. And a crucial feature of, let's say, these methods and approaches is the choice of the smoothing parameter. So the bandwidth defining the smoothing window around the threshold, which determines the observations that contribute to estimate the causal effect.
这个是不是很像那种坐在楼下聊天的那种阿姨？
Can I continue? Okay. Well, okay. And the uncertainty involved in the choice of this bandwidth is never incorporated in the standard errors for the estimates of the causal effects. With our proposal, we kind of embrace a different approach to the analysis of RD designs, which views these designs as local randomized experiments in a neighborhood of the threshold. Essentially, this approach amounts to assuming that the assignment mechanism is probabilistic rather than deterministic, and essentially by formulating a probabilistic assignment mechanism, we can then focus on different causal estimates, namely causal estimates for a specific subpopulation of units around the threshold for which these local randomization assumptions hold. In order to formulate the assignment mechanism in a RD design as probabilistic, we essentially need to view the forcing variable, and this is essentially the crucial assumption, is to view the forcing variable as a random variable. Through the probabilistic formulation of the assignment mechanism, not only we can let's say, focus on different causal estimate for an actual subpopulation of units, but we can also exploit other modes of inference, for example, randomization inference and Bayesian inference, as we will then do in this talk. There are several advantages, but also, of course, disadvantages in this approach to so viewing RDDs as local randomized experiments. But in the interest of time, I will maybe comment on these advantages towards the end of the talk. So a critical issue in this approach, which is mimic, let's say, the problem that also arise in the more, let's say, common approach to that exploits continuity assumptions for the analysis of RDDs, namely the choice of the bandwidth. Here, with the local randomization, within the local randomization approach, a critical issue is how to choose these subpopulations. And again, this is the contribution of this talk in that we propose to use this Bayesian mixture, finite mixture approach to clustering to essentially classify observations around the cutoff point into subpopulations where the local randomization RD assumptions hold or do not hold on the basis of observed data. Again, maybe this approach has also further, we believe, important advantages in that it naturally allows to account for the uncertainty in the subpopulation membership, which is, again, typically neglected also in bandwidth selection. It also does not impose any constraint on the shape of the subpopulation, namely, not all units at a certain distance from the cutoff point are included in the subpopulation that we then use to infer causal effects. It is scalable to high-dimensional settings. It allows to target any causal estimate, so not only average treatment effects at the threshold, but also other estimates like relative risks, as we actually do, given that the leprosy is a rather rare, let's say, event, and therefore relative risks and causal relative risk are, let's say, better describing the causal effect of the Bolsa Familia on this rare outcome. And it's also, let's say, an approach that is robust to certain degrees of manipulation of the running variable, in that we are essentially able to pull out from the subpopulation that we use to infer causal effects units that may be somehow having either confounded or manipulated the running variable to fall around the threshold, and therefore confounding the estimate of the causal effect. Again, this approach can also be used only in the design phase, but again, let me maybe talk about this if I have time at the end of my talk, because I don't have much time. So in order to, let's say, show you the proposal and also possibly show you some result and contrasting them with the usual way of analyzing this data, let me briefly introduce notation, which is rather standard. Z will denote essentially the eligibility status, which again is a step function of the forcing variable. Y denotes the outcome, which takes on value 1 if there is at least a leprosy case in a family. Before assuming SUTVA, we index these the potential outcomes with the forcing variable, so the monthly per capita income. And with this notation, we can now introduce the local randomization assumptions, which include a local overlap assumption, namely, we assume that a subset of units exist, having a non-negligible probability of lying on both sides of the threshold. For these subset of units, we also assume a local SUTVA that allows us to index, let's say, the potential outcomes only with the individual or the family indicator of being eligible or not. We can also then define our causal estimate of interest, which is a local relative risk. And again, this is the main also distinction between the causal estimate in the standard way of analyzing RDDs, namely causal effect at the threshold, because here the relative risk will refer to a actual subpopulation of units, these US0 denoting as US0 here. And again, for these subpopulation of units, another crucial assumption is local unconfoundedness. Namely, we are assuming that for these subpopulation, once we condition on observed covariates, the forcing variable is the distribution of the forcing variable is free of the potential outcomes. And again, our proposal is about how to choose this subpopulation. Typically in local randomization settings, implications of these assumptions are used, and essentially falsification tests are used to select the subpopulation, because under local randomization, we are expecting the pretreatment covariates to be balanced in the subpopulation on the two sides of the threshold. Again, here we instead view the problem of selecting a suitable subpopulation as a clustering problem. Essentially, we assume that each unit or each family can belong to 3 subpopulations, which form a partition of the population of interest. And essentially, we use what we know about these 3 subpopulations to identify or cluster the units into these three subsets. In order to do so, we essentially model the joint distribution of the potential outcomes and the forcing variable as the product, let's say, of 3 joint distributions. And of course, for the population, the subpopulation that we would like to infer, that allows us to infer causal effects, we incorporate the assumptions name, and specifically the Sutva assumption and the local unconfoundedness assumptions into the specification of our model. So I don't know how much time I have, but possibly I'm already out of time here. So maybe let me give you some information, let's say, or the flavor of the type of results that we can get out of estimating these finite mixture models using the Bayesian, let's say, machinery. So here I'm just showing some descriptives that essentially show how different the eligible and ineligible families are with respect to the covariate distribution. And again, those are the specific specifications that we use for the mixing probabilities, the forcing variable, and the outcomes. And essentially, let me maybe go to this point here. So what we can gather out of the estimation of this finite mixture model is, first of all, we can estimate the probability of, or the proportion of units belonging to the relevant subpopulation of units, US0, for which these local randomization assumptions hold. And as you can see here, half of the families belong to this subpopulation. As you can also see here, the number of families, so the subpopulation that we use is, let's say, uncertain, in that there is some variability or uncertainty in the subpopulation membership that is then also incorporated in the posterior variability of the estimate of the causal effects. And again, this is the result that we were looking for. So essentially, this is the posterior distribution of the relative risk. So the risk of having a leprosy case in the family only for the, let's say, units belonging to the subpopulation U as 0. And so these results, even if the posterior credible intervals do cover 1, point to, let's say, a relative risk that it's smaller than 1. And this is also supported by the data with the 80% probability, posterior probability of the relative risk being less than 1. So essentially, the being eligible to the program lowers the risk of having a leprosy case in the family. And again, this is also a result that is pretty different from instead using MSE optimal bandwidth selection, which would point instead to a median, let's say, relative risk, which is above 1. So in general, what we could see, at least from out of these, when analyzing this data, is that the assuming a certain shape for the subpopulation may again end up having a posterior distribution which is sharper than it should be, because it does not incorporate uncertainty on the subpopulation selection, and maybe also be located at a, let's say, wrong value, even if the ground truth is, of course, not known. Yeah, I think that's, again, maybe what I can show you for today. I don't think I even have time for some concluding remarks, but of course I'm happy to get maybe one question before giving the floor to Zichao in a minute. So I think I can, I don't know how it works, whether to take maybe one question from the floor, otherwise just give the floor to Zichao Zhang, who's professor at Sun Yat-sen University. Not sure if I'm pronouncing that correctly. Who will be talking about policy learning with asymmetric utilities. And sorry to have taken maybe a couple more minutes.
Okay.